to start. Demo session is about Teradata, and we're going to specifically talk about indexes in Teradata. Teradata in itself is primarily used as a data warehouse product by many multinational companies and Fortune 500 to Fortune 1000 companies to store terabytes and petabytes of data. They can even store customer data, transaction data, all sorts of historical data for purely analytical purposes to identify a trend. So in that case, we are looking at millions and millions of data. So the major advantages of Teradata is store the data efficiently and retrieve millions and millions of data efficiently, whether let it be a report or you write a SQL script and then export the data. So unlike any other RDBMS, Teradata is a purely MPP architecture, multi-parallel processing architecture. I'm not going to go in detail about the architecture in itself, but I'm going to go in detail about indexes, which is one part of this technical course. The architecture are part of the entire package, but they are different sessions. We cover architecture, design, SQL, indexes, advanced SQL, how to tune a SQL, and utilities. Teradata has a pretty powerful utilities to actually load the data into the database or export the data or manipulate the data or modify or write some logic to actually load these data. So, and then we will also go about disk. I mean, for hardware folks, disk and protection, disk data protection, and all those things. So these are all the basic things that are covered under basic Teradata class. We also teach advanced Teradata for people who already know Teradata. Okay, so let's go into Teradata indexes. This course is for people who know little bit about architecture in Teradata, and other than that, you don't have to have any. There's no major prereq for this course. So when you actually get the full package, you will learn the architecture first, and then we would go into the indexes next. But as part of this demo, I'm just going with the indexes to give you a feel of what Teradata is. Let's go into and look at what is indexes. In Teradata, indexes is one of the most important feature. We will look into in depth of why it is the most important feature. Using an index, you can identify a row uniquely. Using an index, you can identify a row uniquely. Say, for example, you have an employee table, employee number, and employee name. Employee name can be Dinesh. His initial can be R. Another employee name could be Dinesh, but his initial could be B. The employee number for Dinesh, the first Dinesh would be 1. The employee number for the second Dinesh would be 2. which means we are able to uniquely identify these two Dinesh's, even though their initials are different. Because initial would be a separate column. The first name would be Dinesh, initials, middle initials would be his initial, and then his last name. But you don't have to take these three columns to identify it uniquely. You just have to use employee number, which would be an index in this table. So then you can identify the data or each row uniquely. And in Teradata, using index, when you define an index, in this case employee number, the data would be distributed at the disk level, at the AMP level. AMPs are nothing but disks. We will talk in detail about AMPs in the architecture session. So based on the primary index, the data are loaded into the disks, and based on the primary index, the data is retrieved. So if you write a SQL script like select star from employee table where employee number is equal to 1, Teradata is going to know that employee in under employee table, employee number is the primary index. So it's going to look for where this employee number equals 1 is stored in which disk, and then it goes and retrieves the data. That's why index is key. It defines row uniqueness and how do you retrieve the data. Now, in Teradata, there are 5 types of indexes: unique primary index, unique secondary index, non-unique primary index, non-unique secondary indexes, and join indexes. In Teradata, they use something called as hashing algorithm. We're not going to go in depth about this algorithm, but what this algorithm does, we will look at it in depth. Basically, they use this hashing algorithm to distribute rows across the AMPs. What is AMPs? AMPs are nothing but disks where the data is stored. Okay, we will, like I said, we will talk about AMPs in detail in the architecture session, which is a prereq for this course. Let's move ahead to the second page. Okay. There are a couple of rules that are applied when you consider indexes. You should always consider an index. Index could be a column or multiple columns. What I mean by that is index could be just an employee number or combination of employee number, employee name, and employee's address. It can be a combination of these three keys. I mean, the person who's creating the table should decide what should be defined as which column should be defined as an index based on whether the column is able to distribute the data evenly across the AMPs and whether you use that column to retrieve the rows, which means you use this column in the where clause in the SQL. Like I said, you can always have one or more columns in a table that can form an index. And in a table, you should have only one primary index, and you can always have up to 32 secondary indexes. We discussed about this. Columns whose values are frequently used in the where clause or in the join conditions can be defined as an index. So then you can retrieve the data easily if you use it in the where clause, and especially in the join. What is going to happen is if it is in the join, the data is always going to sit in the same AMP, provided the join is on both the PIs, primary indexes. We are going to look at what primary indexes in depth, but these are just the rules. Keep in mind when you create indexes. Always keep these 4 rules in mind. Distribution is important, but retrieving the data is also important. and make sure that your SQL scripts are using these indexes either in the where clause or in the join clause. A table can have only one primary index and can have up to 32 secondary indexes. Okay, primary index, we spoke about data distribution. It is the fastest way to retrieve that data. In Teradata, if you use primary index, for example, employee number, now in our example, we have two Dineshes, but one Dinesh is assigned employee number 1, another Dinesh is assigned employee number 2. If you write a SQL script which says select star from name is equal to Dinesh, right? What's going to happen? It's going to give you two records, and these two records are stored in two different disks because the employee number is the primary index. And when the employee number is the primary index, we will look at how the data is being stored in the coming up slides. But as of now, let's say that primary index is used for data distributions. It's the fastest way to retrieve the data. So if you use in our example employee number equals 1 or employee number equals 2, that's the fastest way than using select star from employee table where name is equal to Dinesh, because name is not a primary index. And it is important for joins as well. We're gonna look at this an example too. So the syntax, how do you define a unique primary index? Is if you have unique primary index within parentheses the column name, and this is what I'm talking about, and then here this is for the non-unique primary indexes. If you don't give unique, by default it becomes non-unique. These are the syntaxes. Okay, so in this case for UPI, let's say that this is a table, employee ID is the UPI. Since it's UPI, which means it has to be unique, so we have a unique constraint, so you cannot have duplicates. So if it is unique, what we need to understand is the data is going to be evenly distributed across the apps. That's really key. If you have UPI, your data is going to be evenly distributed. If it is an NUPI, non-unique primary index, for example, in the same example, you can have last name has NUPI. It is non-unique because if you see Kumar appears twice. So if you have NUPI defined in your table, your data is never going to be evenly spread across the apps. For example, in this case, Kumar is going to appear, let's say, in AMP1. So both the Kumars are going to appear in AMP1, whereas Agarwal will appear in AMP2 and Verma will appear in AMP3. Because AMP1 has two records and AMP2 and AMP3 has just one record, it is not evenly distributed. Whereas in our previous example, UPI, we have 10, 20, 30 and 40. 10 would go to one AMP, 20 would go to one AMP, 30 would go to one AMP, 40 would go to one AMP. These would go to different AMPs based on the hashing algorithm. So all of a sudden each AMP has just one record. So it's evenly distributed because there is no repetition of values in here. 10 doesn't repeat twice, 20 doesn't repeat, so evenly distributed. Okay, so the key is where the row of the table will reside on which AMP. how do you determine that? For example, how do you determine that this row is gonna be stored in which amp? We're gonna look at that. What happens is when a user writes an insert script to insert a record into a table, this is what happens. The parsing engine, um, when you write a script, the parsing engine is something which actually checks the syntax, whether you have accesses to the database to actually insert records. It checks for the basically authority, authentication, and syntaxes. That's what it checks. So let's say you're trying to insert into the employee table. Insert into employee table values. You have value 3, employee number as 3, and then name as Harsha. Okay. So what this parsing engine does is it goes and first checks whether you have the authentication, whether you have the authority to actually insert records. It goes and checks the syntax of your SQL, and then it knows that okay, you're planning to insert a record into the employee table, and the employee table's primary index is employee number. So it examines the primary index. In this case, in the SQL, primary index is employee number, and we have given 3. So it takes the primary index value 3, runs it through the hashing algorithm. The output would be a 32-bit value called row hash value. Let's say that this value 3, employee number 3, which is the primary index, goes through the hashing algorithm, and then you get a 32-bit value, also called as row hash value. So this row hash value determines in which amp the row will reside. In this case, the row, which is employee number 3 and Harsha name. That this row hash value will determine in which amp this row will reside. How does it define? What it does is every row, in order to make it unique, it creates another 32-bit. Now, there's something called as hash map. This hash map, all that it does is it just contains different buckets called hash map bucket. Hash map bucket contains different amp numbers. How does an hash map bucket look? This is how an hash map bucket looks. Say you have a 4 amp Teradata system. The hash map is nothing but it just lists out all the amps 1, 2, 3, 4. So a hash value will point to a certain bucket in the hash map. Let's say it points to this bucket, which means the data is going to be stored in AMP1. That's how we know that the data is going to be stored in AMP1. Basically, the primary index is going to be hashed using the hashing algorithm. It's going to generate a 32-bit value, and then the entire row is going to be given as another 32-bit value. So 32 plus 32, 64-bit. Based on the 64-bit, you decide the amp, which amp it goes through using the hash map. So once the parsing engine completes all this calculation and identifies the amp number, the parsing engine instructs the binet. Binet is the interface between the user and Teradata to send the row along with its unique row hash value to the amp number. So that's how the inserts script, the value in our example 3 and Harsha will be stored to that particular amp number. So this is how a visual explanation. So primary index value. In our case, it's employee number 3. It goes through the hash algorithm. We get a hash value. It goes and looks at the map. Okay, the hash bucket is 346, which is AMP3. It will go insert the data into the AMP3, and then the insert script is successfully completed. We have a lot of theories in here. We already discussed about that. Like row hash and the uniqueness value makes a 64-bit row ID. So then it can uniquely identify each AMP, each row in the given AMP. Okay, next. What is secondary index? Like primary index, we know that is the fastest way to retrieve the data. Primary index, based on the primary index, the data gets distributed. These are the two important things that we know. Also, if you have something as a primary index, try to use it in the where clause or the join so that your query will run faster. What is secondary index? Secondary index is nothing but, let's say, in the employee table itself, we have employee number, we have employee name. Let's bring in department number. In our employee table, we have employee number as the primary index, but I want to look at who are all working for department number 101. What do I do? In that case, department number is not my primary index. What do I do? That's where secondary index comes to picture. Secondary index, what does it do? It provides an alternate path to the data and should be. And you should always, what does that mean is, you can access the data using the primary index, but in our example, we want to access the data using department number. So you can create a secondary index on department number, so then you can alternatively access the data. Rather than accessing the entire table, you create a secondary index to only look at people who have worked under department number 101. So this way, using the secondary index, you can access the data. What are the advantages? If you create secondary index, it will improve the query's performance. How does it improve the query's performance? Simple. Let's say this. If you don't have an secondary index, or if you don't have any indexes on department number, the only way you can actually retrieve the data is to do a full table scan, which means you're scanning the entire table to actually identify just where department number is equal to 101. Say the table is very big. Say we have like millions and millions of records, but out of those millions and millions of records, we have only 1000 records where department number is equal to 101. Is it helpful to access millions of records to just retrieve 1000? And if you are frequently going to access the data using department number, then I would highly recommend to create a secondary index. So then your query's performance is going to increase, because now, rather than doing a full table scan, rather than scanning millions and millions of records to identify thousands of rows, you are going to access these thousands of rows using the secondary index. There is a disadvantage. Now when you have secondary index, you're going to have a space, you're going to consume more space, and there's an overhead. We will look into it. What do I mean by space and overhead? Now, the syntax, there are two secondary indexes, unique secondary indexes, non-unique secondary indexes. Similar to primary index, if you have the word unique in here, which means you are creating a unique secondary index on this column name. If you don't have the unique word in here, by default you're creating a non-unique secondary index. So SI can be created or dropped at any time. Doesn't matter whether a table is populated with records or if a table is something new. Unlike primary index, you cannot create a primary index once, or you cannot change the primary index, or you cannot delete the primary index. But SI, you can create them whenever you want, you can drop them whenever you want, and you can always have more than one SI. When you create an SI, a subtable will be created. What does this subtable have? The subtable will have the secondary index value. This value is nothing but hash value. So this department number data would be hashed, and then you get a 32-bit. And then the secondary index row ID, like how we have the primary index row ID, which makes it unique, which makes it 32-bit, and then the primary index hash value is another 32-bit. Together we form a 64-bit, correct? Similarly, we take this secondary index row ID and then the base tables row ID. For example, this department number would be hashed, and that's the point number 1, secondary index value. This is a department value, department number. Secondary index row ID is nothing but the department number, what all rows are there. That's what makes a row ID. And then the base table is nothing but where is the employee, employee table is as employee number, employee name, and department number. Where does department number 101's base table rows, which are distributed using the employee number, where are these stored, is what we are going to look at. But that would actually make this point number 3. Now, if you create a subtable, it requires perm space. As discussed, if you create a SI, make sure that that column is frequently used in your where class. The architecture, say you're going to create an unique secondary index on social security. So in this table, you have employee, that's the primary index. You're going to create a social security secondary index. Now the row ID is for this entire thing is 04,1. That's the row ID. Now you would hash this, you would get a hash value. That hash value plus this row ID determines in which AMP this row would be stored, this base row. Now coming to the secondary index, you will hash this value. That would form the secondary index value. Now the 102,1, that forms the secondary index row ID. And then the 45,1, for example, in here 65 is the primary index, so that would form the 32 plus the uniqueness 32, correct? That's how you're going to determine the which AMP is going to store. What did we say is we needed secondary index value, secondary index row IDs, base table row ID. This is what the subtable will consist of. So you have the secondary index value, secondary index row ID, base table row ID. The reason being, in our example, let's say you want to query, I want to know which employee number has social security equals 276682130. So I'm going to write a simple script. Select employee from employee table where social security is equal to 276682130. So using the secondary index, it is going to go to this thing, these three things. It is going to say that, okay, this is stored in AMP2, but the base row ID 276 is 0401 041 is actually stored in AMP1. How do I identify all these things? Using the hash map. Once I have this value, I'm going to go to the hash map to actually see where does this value, in which AMP does this value reside. That's what I'm going to do to actually retrieve the data. So now the concept here is, even though we are planning to access the data using the secondary value must be related to the primary or the base. Even though social security is our secondary index, there is a secondary index value, it should always be linked to the base table. Secondary index will always be linked to the base table. That's the thumb rule. Now what happens? You're going to write something like this. Employee number is equal to 56. It's going to row hash it. Once it's row hashed, you're going to find out that, okay, it's an AMP number 2. It's going to go to the AMP number 2. It's going to say that, okay, this AMP number 2's row ID is 778. And then I'm going to go to the row ID and then I'm going to retrieve all these values. Boom. USI is always a 2 AMP operation. The reason being, first the parsing engine has to read the subtable which consists of the secondary index value, secondary index row ID and the base table's row ID. Once it reads that subtable, it's going to know where the base tables rows are stored, in which AMP. Once it knows that, then it has to go read the base NUSI. The major difference between USI, unique secondary index, and non-unique secondary index is, in unique secondary index, there is no guarantee that the subtable records are going to be stored in the same AMP as the base table rows. There is no guarantee. That's why it's a 2 AMP operation. But in the NUSI, the subtable will be built on the AMP local, which means each AMP will build the subtable in its own base table. What does this mean? If we have employee number, employee name, and department number, and let's say, I'm going to say, for example, we have employee number, name, department number. Okay, we have employee number 1, we have Mark, and then 101. 2, we have Dinesh. We have 101. 3, we have Mike. 102. 4, we have Don. 103. Okay, if we have USI as department number in our table and PI, which is an NUPI, as employee number, what's going to happen is the data is going to get evenly distributed for this employee table. This is an employee table. The data is going to be evenly distributed because this is unique. But when you define an department number as a non-unique secondary index, because we have two 101s, you cannot create an unique secondary index because it's not unique. If you create a non-unique secondary index, what's going to happen is, let's say that we have AMP1, 4 amps, and employee number 1 is stored in AMP1, 2 is stored in AMP, like that. Okay, we know that how it is going to be stored is it goes through an hashing algorithm. We get an hash value, combine that with the row ID, we can determine that in which amp the data is gonna be stored. We can look at that in the hash bucket, right? Let's say, for example, that employee number 1 is stored in employee AMP1, employee number 2 is stored in AMP2, 3 is stored in AMP3, 4 is stored in AMP4. What's going to happen is, if you create an NUSI, this first record 101, because we know that NUSI is going to, the subtable for NUSI is going to be stored in the same AMP as the base table. Now the base table 1 is stored in AMP1. So this 101 is going to be stored in 101. This 102 in here is going to be stored in AMP2. This 102 is going to be stored in AMP3. This 103 is going to be stored in AMP4. So when you query a table, when you query using NUSI, what's going to happen is, say for example, I want select name from employee table. Let's say select name from employee where department number is equal to 101. What's going to happen is, this is going to look at all the amps, but and then determine that, okay, 101 is only stored in AMP1 and AMP2. From there on, it's going to go to the base table using the base row ID, and then retrieve this name Mark and Dinesh. How it is done is, we'll see here. The secondary index has a subtable. The NUSI has a subtable like this. Now John is the NUSI. Let's say John has a secondary index value, and then it has a secondary index row value. Now John's primary index is 88 in here, so it would have two row IDs, which is 04, 01, and then 25, 1. Okay, and then 18. So now this secondary subtable, index subtable, will appear in all the amps. So when they query, it will go to 04, 1, 25, 1, go look at the hash amp, and then get the amp number with, and then retrieve the data. That is why it sometimes NUSI can be an all amp operation, because you never know this John in here can be stored in more than 1 amp, because John will be stored in the same, this John subtable will be stored in the same place where the base tables are stored. In this example, pretty sure it will be stored in at least 2 amps, at most 2 amps, correct? This both can be pointed to 1 amp, these both can be pointed to 2 amps. So NUSI will create a subtable on all amps. Each amp will hold the secondary index value for their rows in the base table only. So subtable will be created in all amps, but each amp will only hold the secondary index values where it corresponds to their base table rows only. Each amp will have a base table row ID so that the amp can retrieve the data quickly. NUSI is slightly different than full table scan. Reason being, the parsing engine will decide if NUSI, if it is strongly selective and if it is worth using over full table scan. Full table scan will actually access all the amps, whereas an NUSI, if it is selective, it doesn't have to access all the amps. It could end up accessing just one or two or more than that amps. Maybe it needs to access all the amps if if it is not strongly selective. Okay, let's look at how the NUSI is going to work. Let's say the same query, NUSI is going to give you 602. Now if you see, it's going and looking at all the amps to actually retrieve, to go to the 602 and then retrieve it. Okay, whereas USI, it was 1 amp operation to go retrieve the subtable. The major difference between USI and NUSI is in USI, it goes through the subtable, which will be in 1 amp. From there on, it will go to the base table amp, which will be another amp. So USI is always a 2 amp operation, whereas an NUSI, it could be an all amp operation, because it would go through all the amps, try to retrieve one particular value. Okay, what is partition primary index? We saw primary index, we saw secondary index. There's another index is called as partition primary index. What does it do? It basically splits the table into series of subtables. What does it mean, series of subtables? So partition, which means it's going to dissect the data into different layers or different containers, or it's going to put some data in one container, it's going to put some data in another container. That's what partition means. So we're going to look at an example here. In the order table, order ID, we have cust ID. Cust ID is the primary index. We have order date. We have partitioning based on the order date. So now, cust ID, using cust ID, the data is going to be distributed. But inside the cust ID, we're actually partitioning by order date. So, and we're going to give that we're partitioning between this date and this date for each interval 1 month. So in cust ID, it is distributed. All these order date will be clustered per month, and every month will form a partition. Let's see how it is going to work. Before that, what is the use? Performance. Rather than doing a full table scan, if you use PPI, you may end up consuming just one partition. Let's see how that works with an example. There are advantages and disadvantages. Advantages is like always, you're gonna read the data faster. It improves the queries performance. What's the disadvantage? Whenever you use PPI, your table size is going to increase by 2 bytes per record because PPI rows are 2 bytes longer. So it's going to consume more PERM space. The same is applicable even to secondary index. When you define a secondary index on a PPI table, even the subtable rows are going to increase by 2 bytes. Okay, so primary index. Primary index, I'm going to take another example. I'm going to give you this example. Let's say you have primary index as this one. Order ID, cast ID, order date, and order amount. Okay. Order ID is 1, 2, 3, 4, 5, 6. Cast ID is 0, 1. 02, 03. Okay. Let's make it 7, 0, 1. Okay. Order date is going to be 2012 01 01 2012 01 10. 2013 01 01 2012 03 01. Gonna be $1 $1. So let's say we have amp 1 3. I'm sorry there. Now we have primary index cast ID, correct? So we have cast ID 101, 102, 103. So 101 is going to be stored here, 102 is going to be stored here, 103 is going to be stored here. So we're going to have this and this stored in AMP1, correct? When you define order date as a partition, how it is going to store is, it's going to basically make a partition. Let's say that 101 is stored in AMP1, but it will be a partition. What do I mean by that is, and the partition interval is 1 month. So in a year it's going to have 12 partitions because we have 12 months. So these two Jans, Jan 2012, it will come under one partition. This March will come under another partition. So 1 comma 1 2012 1 2012 3 slash 1 slash. The way it's going to work is it's going to have these things listed in one partition and this as a separate partition. So when you create a partition table, it's going to sort the rows and keep all the 2012 Jan under one single partition. If you don't have this partition, what's going to happen is, let's say you write a SQL like select star from order table where customer ID is equal to 101 and order date between 2012 Jan 1st to 2012 Jan 15th. What is going to happen in a table where primary index is not defined? What is going to happen is it's going to know that okay, 101 is a primary index, it's then in AMP1. But since there is no partition, it's going to scan these three rows to check whether the order date is between 2012 01 01 and 2012 01 15. It's going to scan these three rows to check if the data is between these two, then retrieve. Because the data is not partitioned, we are talking about a table with no partition primary index. With a table with no partition primary index, it will go to the AMP1 because of the 101 customer ID being the primary index. This equal, it will know that, and then we'll scan these three. It'll say, okay, this is between this, okay, pick this. This is between this, okay, pick this. This, it's not between this, then don't pick this. So unnecessarily you are reading more records. Now, when you have partition primary index, it's really simple because it is partitioned. Now, if you give this and then you go to an AMP with 101, you know that this record, because it is partitioned by 1 month, you know that it will only appear in one partition, so it will just go read that partition and then come back. It won't even read this. Okay, so that's a huge performance benefit. That's why they say you can retrieve the data faster. Correct? You can retrieve the data faster. It improves the performance. Okay. Look at what the partition primary indexes is. Let's go ahead and look at what join indexes are. What is join index? Join index is nothing but when you join two or more tables and then you keep the results set in permanent place in Teradata, which means you're creating a separate sort of a table which is consuming the perm space. But the input for that is two or more tables joined together, and you're storing that result in a separate table which is called join index. Anytime you create a join index, parsing engine is going to determine whether to actually retrieve the result from the base table or go through the join index. Even though you create the join index, parsing engine will determine whether to use the join index or not. There are three types of join index: multi-table join index, single table join index, aggregate join indexes. What is multi-table join index? So this is the syntax. I'm going to create join index, the join index name as select all these column names from employee table. This is the first table. Inner join department table. We're going to join this on employees tables employee department and department tables department number. You have a unique primary index employee number. So this would become a multi-table join index. So anytime you want to retrieve records from employee table and department table, then the optimizer could use this join index and retrieve it faster. Basically what it is doing is it is putting all these select statement, the data from this select into this join index, which is going to be distributed under AMP using the okay. So that's why it's going to consume perm space. And also any change made to the employee table or the department table, the optimizer or the parsing engine would automatically update the employee underscore department's join index. Since we are using more than one table, it is called as multi-table join index. Now, single table join index is nothing but, okay, the employee table's primary index for the employee table is employee number. We know that. Now I can create a join index which is going to select the data from employee table, then distribute it based on the employee department. So anytime we write a SQL script which actually tries to retrieve the data using the employee department, the optimizer could use the emp underscore snap join index. It's up to the optimizer whether it has to use the emp underscore snap join index or directly use the base table employee table. It's up to the optimizer. What is an aggregated table join index? Now, if you use an aggregation like average, max, sum, count, if you use that, create a join index, then it's called as aggregation table join index. So if you write a query which is select department number, comma, average, employee salary from employee salary, then the optimizer could determine, do I go to the base table employee salary and then calculate this average salary per department, or do I go to the join indexes agg underscore table created and then retrieve this data. Now, a couple of things. The join index is not a pointer to the data. It actually stores the data. Okay. Primary index is a pointer to the data, whereas join index stores the data. Next, users can never query them directly. The parsing engine decides whether to use them or not. Third, whenever a base table is updated or if the data is changed in the base table, then the join index is updated. So there is an overhead, right? So if the base tables are frequently updated or the data is changed in the base table, then the join index is automatically updated. It's something like the secondary table, secondary indexes, where you have a subtable. Now, if you insert or update any record in the base table, then the subtable also needs to be updated. Similarly, the join index, if there's any change to the base table, join index will also be modified. Next, another big thing. If you have join index defined on a table, you cannot use fast load or multi-load utilities. So you need to be really careful when you use join index. Next is questions. I mean, any questions